Students, welcome back to the lab. Today's lab is a bit different than the ones we've been doing. In my opinion, you've had it easy up to this point, so hopefully you're prepared for it. But the lab today is using a different software, and what we're going to be using is CLIA software. So if you're going to come to class for this, navigate through your start menu, find CLIA exercises, and then it is the Stellar Spectra exercise. Also, if you haven't read through the manual for this one, definitely read through the manual. It is a long lab. The beginning talks about stellar spectra, and there's lots of stuff in there that just can't be covered in a quick introduction to this sort of thing. This will all be longer than usual, but hopefully it's a bit more involved and fun than our usual exercises. Also, if you haven't covered this in class, the spectra of stars and why that's important, reading through the manual will help that even more than the introduction will. All right, so here we are in the CLIA software, and where we're picking up in the manual is on page 7, part 3, spectral classification of main sequence stars. So the first thing we need to do is log in. So it would want all the students' names. So me and you will be the students, and we will be table 1. Yes. And this brings us here to where we can run the first part, take spectra. And what this gives you a glimpse into is what it would be like controlling a specific telescope. So you now have control of the 0.4 meter or 16-inch telescope, which is a good sized telescope. You can also go here to which telescopes you have access to. Right now you have access to the 4.4 meter, but you can request access to larger telescopes. So the maker of this wanted you to feel like a real researcher, where you don't really have access to the best of the best unless you have something to show for it. There are also a few options you can play with, and this is one of the more fun ones to see in class. So you open up the dome, and now you have a view through the finder scope of your telescope, and if you look closely you can see that the sky is moving because tracking is not on. So if we turn on tracking, now the telescope will remain pointed at these specific points in the sky, and we can move around similar to what we've had, except some of the controls are the exact opposite of what we've been using on other things up to this point. And if you find a star that you like, hopefully a bright star, you can center it with your finder scope and then switch view to your instrument or your actual 0.4 meter telescope. Then you can go about centering that between the lines, and you can take a spectrometer reading, which is basically just looking at all the photons entering your telescope and classifying them by wavelength. So for each photon that enters your telescope at a given wavelength, this box, you get one higher intensity, and once the telescope becomes saturated, it starts to filter out. So there's still hits coming in for these areas and these areas too. There's just less here. So this has a greater proportion of photons coming in than this area. And the longer you let this run, hopefully the better your signal is. So the signal is the big features and other things that are not bouncing around. The noise is things that continue to change. So little areas like this, but hopefully as we collect more signal, we can filter out the noise and this will stabilize. So we saw that after a few seconds, all of the big features were pretty much stable, all of the peaks and troughs. Some of these little features took longer, but they get more and more stable as you take more and more photons in. And then we can stop our count. We could save this spectrum, we could print it, we could do pretty much whatever we want. We won't do that quite yet. So we've returned to our telescope, and now we will get into the exercises. So the first things that they want us to do are to go to classify spectra. And in this, we want to go to an unknown spectrum, and we just want to take the first one. This is HD 124320. And what we want to do is look at a few things on this. So right now we are moving into page 8. We have our spectrum on screen, and when it's on screen, we can do a few things. Basically, if we click around this plot, we get a few numbers that come out. So if I hold the crosshair down, it will give me a measured angstrom, or the wavelength of the photons that created this trough. The intensity, so down here, very low intensity. There's hardly any photons hitting for these wavelengths. And up here, the highest intensity, there are quite a lot of photons hitting. And then it also gives us which display we're talking about. So if I click down here or up here. What it wants us to do is two things. First, it wants us to choose any point on the continuum of this spectrum and write down the wavelength and the intensity. So I'm going to click this little peak here, and the wavelength and the intensity are displayed here. So if I very precisely try to put my crosshair right there, this is the number you want to put in for A. So on page 8, question A, measured wavelength, measured intensity. And your wavelength here is in angstroms. So an angstrom is a tenth of a nanometer. So if you want to convert this to nanometers, you would move this decimal point right there. For question B, measure the wavelength and intensity of the deepest point of the deepest absorption line in the spectrum that is displayed here. So before starting this up, I measured these three major troughs here, and apparently this one is the deepest one. I don't know why that was. Maybe not. All right, we can do it in class. So the intensity for the deepest one would be the lowest. So if I line this up right on the peak there, we have an intensity of about 0.31. This one here, can do it this way too. The intensity is about 0.29, and this one here, also about 0.29. I'll go with this one just because it looks deeper. All right, so this is what you want to put for B. What measured intensity and what angstrom reading that was at. And it is a bit different than what I had a second ago, but go with these numbers here. All right, and then the question C, if you looked at this range of wavelengths with your eyes, what color would they appear? So basically, what color do you see as between 3,900 angstroms and 4,500 angstroms? Again, converting this to nanometers, this would be about 390 to 450 nanometers. But basically what you need to do is look up some sort of spectrum and see what color is represented or is closest to those. And it might be a range of colors. If it's between yellow and green, right down, it ranges from yellow to green, or whatever it actually falls into. But that's the range you're working with. Look that up somewhere and write down whatever answer fits best. So the next thing that they want us to do is to find a spectrum to compare this to. So by going to Atlas of Standard Spectra, I believe all we use will be the main sequence stars for this lab, but basically it gives us representative spectra of different stars on the main sequence. So O, B, down is A, F, G, K, and M. And we can go through these by just hitting the down button. And what we're looking for is the closest spectra. So a few things change as we go through this. Probably the easiest to notice is the size of the peaks, as well as the number and the placement of peaks. So here, this peak here is developing. If we keep going, that peak becomes a major peak, and some of the other ones that were larger seem to disappear. And this is because of what's being absorbed in the photosphere of these stars. Remember that anything that shines gives off blackbody radiation, and that tends to be a very smooth curve where the peak moves up and down the wavelengths depending on how hot the star is, but it's smooth in between where the peak is. So knowing that, we know that these absorption troughs must be in the photosphere somewhere. The other thing that we know due to blackbody radiation is that the peak should be moving, and we can kind of see that maybe looking over here. So the brightest intensities for these M-class stars are on the very right. Those are high wavelength peak emitting stars. And if we go up the chart, the peak appears to move to the left. So for these, it appears to be right in the middle somewhere. And if we keep going up, we can see that these, the highest intensity, are further left. So if we were to go all the way to the top, to the B-class stars, we could measure this point here as the highest intensity. It has 0.98 intensity, and that is measured at the lowest wavelength there. We could also go down, try to find one here. The highest intensity is somewhere around here. I'll just say it's there. As we go down this list, we will see that the peak intensity moves further to the right. And then the last feature of this is the bottom graph here, which is the difference between the two. This one here, and I might have skipped ahead to the answer by doing that, but you can turn on the difference or have it just mirror the top. The difference makes everything a lot easier. Basically, you're looking for the standard that looks the most like our mystery spectra, and by doing that, we're looking for the least difference between the two. So as we go through these, we can see that as we change, certain things will get closer. So as this peak gets a bit smaller and this peak gets a bit bigger, we will see less difference in that area. And as we go on to the correct match here, which I believe is A5V, and V means main sequence, that we have very little deviation from the zero difference here, meaning that these two are almost identical. And if we continue going, A1V might be the correct answer. But that's why it's useful. So when I was looking at these, I mostly looked at this peak here, which does appear to fit better in this standard here, but everything else actually fits much better in the A1. So A1 would be the correct standard to match this to. And if we continue the other way, we will see different parts that match worse. So like I said, A1V seems to be the correct answer. This one here is close, but not quite the same. But they are both in the A-class stars, so they're quite similar to begin with. All right, so moving on to page 9. Hopefully you're reading along, and we come to Wien's law, which states that the wavelength of maximum intensity is shorter when the temperature of the object is hotter. So what that means here is stars that have the peak intensity further to the left will be the hottest stars. Which brings us to question A on page 9. As you look through the stars in the atlas, can you tell from the continuum which spectral type is the hottest? Identify the hottest spectral type. And again, as we went through a moment ago, basically as we go up this list, the peak intensity moves left. So which star is at the top of this list, basically, and that should bring your attention to the O5 star. Explain your answer. Remember that on these graphs, 3900 angstrom is at the left. Just double check. Yeah. And 4,500 angstrom is at the right. So how would you explain your answer? Well, what did you see? Which is the peak intensity here, and what does Wien's law say? At about what spectral type is the peak continuum intensity at 4,200 angstroms? So it's about the middle of our axis here, so 4,200 angstroms. So I'll go through this list somewhat slowly. You can go through this video multiple times. So when you see one that has a peak intensity right about here, that is, and I can turn that on the bottom. So this is the same as the top. So when you see the peak intensity right about here, that is the one you will want to pick. And I'll just go through these. Again, the highlighted one on the right is what we're currently at. All right, so hopefully those last few aren't your guess, nothing in the M class. But if you are having trouble, maybe estimate there are probably 2 or 3 in there that could have been candidates, and really if you picked one of those, it's probably fine. But something to look for is it's not here, it's not this one, it's not this one, it's not this one. Some of these are close, and it's not these either. So pretty much in the middle there, which one do you think it is? And then question C, what is the temperature of this star? And to find the temperature, we will need to find the maximum intensity. So to go about that, you would basically go back, and this, I guess, is impossible to do without knowing which one of these it is. So I think it is this one. Yeah, I believe it's this one. And the peak would be somewhere around here. So intensity is 0.99 at 4164. So that is what we will want to use. We will put that into Wien's law. So we know that our lambda max is the 4164 angstroms. Put that into Wien's law, which is given on page 9, and solve for T, and you should get an answer for the temperature of that star. So moving on to page 10, we can basically get to the point where it asks us what spectral type our mystery star is. And we've already gotten to that point, but we will go back to it. Again, A1V, that's the answer to the question in the middle there, what is your estimate? But you will need to come up with reasons, and I'm saying reasons, so more than one reason. Do not just say the difference was the smallest. Why this is your choice. And if you did pick A5V, this is a fine choice too, but give reasons, give multiple reasons why this is your choice. So what reasons might you have? Well, I mean, they look quite similar, but give specific features that you're looking for. The difference could be one reason, and it is a very good reason, but it is not always perfect. So definitely looking at small features of these, there are differences. So give a few reasons why you think that these are closer than any of the other ones. All right, so we talked about using these lines to identify stars, and we briefly mentioned where these lines come from. So again, it's light being absorbed in the photosphere by different things or different atoms. Now we get to find out which atoms those are. So this is a list of spectral line identifications for what each atom or each group of atoms will absorb. And what we can do is kind of pick one, double click it, and it will put on here a line of where that absorption happens. So if there is a lot of, I don't know what MN is, there's a lot of helium, there would be a big line here, a big trough here of where the helium is absorbing a lot of the light from the stars. So if we go through these, we should be able to find one that has a lot of helium. Well, this one has at least some helium absorbing the light in the photosphere of the star. What the handout wants us to do is look for a specific one, or a specific trough. 4341 is the one they tell us, which I believe is right here. And what line is that? So that is the hydrogen line. Most stars will have a hydrogen line, because as you know, hydrogen is what fuels stars. There's hydrogen all around stars. Almost everything is made of hydrogen. So it makes sense that most stars will have a hydrogen line. All right, the next step is to identify the line that occurs at 3,933 angstroms. So there's two ways to do this. We could go here and click around until we're at about 3933, which I believe is this peak here. Or we could go directly to our list. That is the calcium 2 line or the K line. So top of page 11, that is what you are looking for there. So if you've seen a spectrum that has been taken or given for educational purposes, usually it doesn't look like this. This is a very good way to take a spectrum. Again, like each tick mark on here represents a hit at that photon and at that photon intensity. And the higher up the line is for each wavelength, the more photons have hit the instrument with that intensity. But it doesn't really translate well to seeing what's going on. So what we can do with this software is change our setup to, let's see, grayscale photo, and now it is a bit different. So we can see the dark areas, there is little absorption happening. The light areas, there's a lot of absorption happening, so we're getting a lot of photons in these. The one that might make more sense is photo and trace. No, that isn't it. Isn't there a colored one? I guess not. So we can't make it fun. So I'll leave it on grayscale. But you could imagine that this would be the rainbow spectrum here, and these would still appear dark even in that rainbow spectrum. So the spectrums you might be used to seeing in class. All right, so for page 11, the bottom two questions. First, give a physical description of the absorption lines in the photographic spectrum. So that is this spectrum here. What do the absorption lines look like? We did go over this, so just explain how the absorption lines, which are these areas here, here, and here, and here, are different from the rest of the spectrum. And then the next question is with the trace that we've been working with, what do the absorption lines appear as? So here, 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 and here. How would you describe those? All right, and this could be important because if you were just given a blank spectrum and you didn't have the tools where you could display them right next to each other, or you could have the computer calculate a difference between two spectrums, you might describe it to someone based off of these absorption lines. You would say where they're at, how big they are, or if you were just given one of these, how wide they are, and how dark they appear compared to the rest of the photo. So you would want to be able to say both something about the intensity, something about the wavelength, and something about the overall size of these. All right, so if we were doing this and we wanted to get as accurate as possible, like I said before, this sample spectra seems to be very close to A1, but A5 also has some features that seem to fit a bit better. So what we would do then is go to a different list of spectra, find the luminosity we're closest to, so A3 is in the A class at least. and then from here find the one that fits the best. So of these, this one is not bad at all, but this one is probably the closest. This one here, I don't think is great, so I would go with A33. But for today's lab, we are probably not going to be doing that. We're going to be sticking to our main sequence stars. And if you are on page 13 of your handout, you'll see a huge list of stars. Those are all our sample spectra. And basically what they want you to do is classify these stars. I am not going to do all of these. I'm going to do a few of them, and basically in the same way that we saw before without making it too easy on you, so the difference won't be on. I will go through the main sequence stars for a few of these, and you will need to pick which one is best and give at least 2 reasons for each one why you think that is. So not exactly randomly on the ones I'm going to pick, but you'll see them when they come up on screen. I will pick a few different ones. So we've already done HD 124 320. I'm going to do 1, 2, 3, 4, 5, 6, 7 of these. All right, so follow along with me. We will not go through them in order. So the first one we're going to do is HD 23733. HD 23733. Again, that's our middle one here. I close that. It's not really needed anymore. So now I'm just going to go through this list. Look for the one that fits best. And again, you can rewind this video as many times as you want to find ones that you think look the best. All right, hopefully you saw one that you thought was correct in there. I'll give you a hint, it's not these bottom few. So write that down now, which one you think it is, and pause the video and write down some reasons. So hopefully you've done that. This one, I will give you first what I think and then what the difference thinks. So I think this one is very close to F5. F0 fits pretty well too. It could be F0. We'll see what the difference is. Yeah, I'd probably go with F0. However, if I couldn't turn on the difference for this, I probably would have picked F5. And the reasons I would give for that are, first, it has 4 major absorption lines. They all fall in the correct places between our standard and our sample. And they look to be about the right size. So this one, maybe, these 3 all seem about right. This one might be better down here, oops, or up here for F0. Yeah, so that one seems about right, but this one seems different. So I tend to look at the left side because I think it changes more. So you can put examples like that. For example, there were 4 major absorption lines, and you could pick a specific one that fit the best. So I believe for F5, this one seemed to fit the best. These 2 don't change much between the 2. But if you were picking F0 and you didn't have the difference to tell you, you'd probably point out that this one matches a lot better. So that's the type of stuff we want for your reasons. So again, HD 23733, either F5 or F0 would work, but F0 is probably the more correct answer. All right, the next one on the list that we will do is HD 107399. HD 107399. That's the middle one here. Again, we will just go through the list top to bottom. You can watch it as many times as you want. I won't turn on the difference or give you the answer or the accepted answers for this one. All right, so that is the list. Feel free to go through that one as many times as you want to find whichever one you think is the match. And it might seem like a lot, the whole list they give you in class, but really as you do these, you can kind of see when you're approaching the right one, and you can usually narrow it down to 2 or 3 choices. So the next one is BD plus 63 space 137. That's this middle one here. Again, we're just going to go through the list, and you can write down which one you think it is and the reasons why you picked that. As we do more of these, you should also kind of get a feel for which end of this list the answers will be at, or the more correct answers will be at. All right, so at the bottom of the list, I believe this one might be a bit trickier than a few of the other ones. There's no like glaring differences between a few of them. So whichever one you pick, make sure to back it up with specific reasons. So specific parts of the standard and the mystery spectrum that you thought matched better than the other ones. All right, so the next one we're going to go with is phage 41. Phage 41. Again, that's the middle one here. We'll go through the spectrum the same way. And again, all right, that's all of them, so whichever one you think fit best. And within each of these, we have one on the hot end of each classification, one on the cool end. Right? No. Hot end, cool end. So there are specific subcategories that would fit better for a lot of these as well. So again, you're just picking the one that you think fits best for specific reasons that you're given, and as long as your reasons are valid, that should be fine. SAO 81292 is next. Again, that's this one here. So hopefully you went through that enough times to find one that you thought fit the best. Next spectrum will be HD 27685. All right, top of the list. And we'll go through them all again. All right, on to the last one, which I believe is just the last one on the list. HD 158659. All right, here we go. All right, so that is the table for page 13. So hopefully you were able to fill that in. Otherwise, go through the video again. As long as you're close, usually there's some wiggle room between maybe two answers that you could have here. All right, on to page 14, which we're not really going to do. Basically what you would do if you wanted to go through that is we would pull out our spectral line table. We would pull up all of these and we would identify what these specific peaks actually are. So this one would be our calcium. Maybe this one and this one we would also identify. And then go through and do that for everyone. So some of these have much more pronounced lines. So the hydrogen line, the calcium line, the other hydrogen line. Let's find one that's a bit different. Maybe this here is an interesting thing. So somewhere between iron and calcium there. Maybe this here. You would go through and you would basically pick the biggest features and then write them down for each spectral type and the wavelength that goes along with them. However, a similar chart can be found in the appendixes of your handout. So on pages 20, I guess just page 22, it tells you which lines are strong, and if you know where these lines appear, you could go to this table here and find them. So if you weren't even given the spectrums over here, but you were just told where the lines appear or even what is in the photosphere of these stars, you could probably start to determine where the absorption lines should be, and then from that look at some standards, and from that you'd get a good guess of what the star is. So we're not going to do that because it would just be me reading these things off to you and you writing them down. So skip page 14 is the moral of this part of the lab. So what we've done up to this point is more or less background at part 4 of what we are at in our lab manual. So this is page 15. This is where the lab itself would really kick off. So the point of this is to give you as realistic an idea as possible what it would be like to look at a star and take a spectrum of it and then try to classify it. So again, we have our dome. We can open our dome, which will give us a view of the night sky. And we can begin making our observations from that. All right, we would move around the same way I talked about before. We could change our slew rates. We can move very fast, even faster, or very slow. 4 is a good number. We can center a star, more or less. Change view. Again, center. And from that, we could take a reading. And at least in my experience, this is a pretty realistic idea of what your user interface would be on a 0.4 meter telescope. With bigger ones, could be more or less things. The only thing different from the telescopes I've worked on is the dome is opened by a person either turning a crank or hitting a button. Everything else is pretty similar. So when we're at this point, we can again go back to our star and take a spectrometer reading. So again, as photons hit our instrument, they are registered by their wavelength. The more that hit at a certain wavelength, the higher this line goes. The less relatively that hit at a certain wavelength, the lower, or your absorption lines will appear there. All right, so the first thing that the handout wants you to do, this is on page 17, is to record the position of this star, and that's given by the right ascension and the declination. If you haven't learned about this in class, basically it's just the coordinates in the sky where you would be looking for this. And also the apparent magnitude, so how bright the star appears to you. So this telescope gives all of those. Apparent magnitude might be the only one that's not really given, but it's not hard to get that from a telescope. Basically, it's adding up all of these all of the photons, not classifying them by wavelength. So write those three things down on the top of page 17. And we've already done the next step, which is to take a reading. All right, so just like what we did before, we can work with the spectrum. We can record what it looks like, and we can also find the wavelength and intensity for certain absorption lines as well as certain peaks. So our peak is probably right around here, and then there's these four main absorption lines. And if I'm looking at this, it does look a lot like the first one we worked with, which is not on purpose. It looks a lot like HD 124320, which was a type A3 star. So if we're already making guesses as to what this spectrum might be, I would say an A-class star is a good place to start. All right, so now what we need to do is save our star name, enter the number ID of a star. I will just call it 1. There we go. File will be saved as 1. We can record that if we want on page 18, but basically we need to do this so we can pull it up against our standards and try to classify it. We can now return by hitting return, and this will exit our specific spectrum and bring us back to the telescope. Once we're at the telescope, basically we should just find a different star. I want this very bright star up there, so what we should see is the apparent magnitude change, and hopefully we'll see something else change in the spectrum as well. And I believe, hopefully we only need 2 stars. All right. And this works quite well for single stars, so if you know you have a single star that you're looking at, taking the spectrum can be easy. If you have some sort of double star system, which many stars are at least 2 stars, it gets harder. So I believe the system here is set up mostly for single star systems. All right, so on page 19, the things we want to record are the right ascension, the declination, and the apparent magnitude, which it seems is lower. Oh yes, that makes sense, right? If you know which direction larger, brighter objects appear on here. All right, to conserve telescopic resources, no further integration of this spectrum is allowed. Cool. So this is the spectrum we get. Again, we'll save it. This one we will call 2. And we will need to remember that that is the name of that spectrum. All right, so make sure you have the apparent magnitude, 4.03, right ascension, 6 hours, 14 minutes, 20.61 seconds, and the declination, which I believe is 33 days, 21 hours, 30.2 minutes. I don't know why they made them different units there. All right, so we have this saved as 2, and now we can return. Yes. All right, and work on the next part. So basically what we want to do now is go back to our classification of spectra. We open a saved spectra. Spectrum 1, that is right there. That's our mystery spectrum. And then also open our main sequence. And we'll do this the same as we did for the other ones. I will go through these, and you can go through this video as many times as you want. Pick the one that matches most closely. All right, then we'll do the same with our spectrum 2. And these will be going in the table on the middle of page 19. So once you've picked the spectral type that you like, again, just the first two, so O5 or B6 or F, whatever. That's all you need to write, but give 2 reasons why you think that's the correct spectrum. So this is our second spectrum, spectrum 2, and again, we're just going to go through these. All right, and it should have been one of those, and there might be a few that it's close to, so that's where your reasons for picking each one come into play. All right, so once we have those 2 stars classified, we're pretty much done taking data. So that brings us to page 20. So on page 20, there's another table. The first 2 parts you can fill in. The star, we have star 1 and star 2. The spectral types are the 2 types that you just found. And we could also fill in the apparent magnitudes. So the apparent magnitudes were on the previous pages. Those were given by the telescope when we pointed at these stars directly. So when we have that, what we can do is find the distance to these stars by the equation given on the top of page 20, which is known as the distance modulus. Basically what the distance modulus is it gives us a way to find how far away a star is because we know how bright these stars should be. So an example is if you know how bright a regular candle is, you can pretty much tell how close you are to that candle by how bright it appears to you. So most people know about how bright a regular candle would be. If this candle is 100 yards away from you, it would be dimmer than if it were 2 yards away from you. And you could make a guess as to how far away the candle is based off of how bright it appears to you. So that's what the distance modulus is doing. So the variables we need to put into this equation are first the apparent magnitude. This is the little m, and that's the numbers that we got previously from the telescope. And the other number that we need is the absolute magnitude. So again, this is a number that we know for stars of a specific class. And you're given one of these in your handout. So on page 23, for each spectral type, you're given an absolute magnitude of these stars. And that absolute magnitude is how bright the star would appear in our sky. So the apparent magnitude if the stars were all at a distance of 10 parsecs from us. And by finding the distance between, or the difference between these 2 numbers, we can get a good idea of the actual distance to these stars. So again, find the spectral type for star 1, go to page 23, look in what should be the, let's see, main sequence stars, supergiant. Yeah, so look in the first table, find whatever spectral type you classified that as, and then find the absolute magnitude. Write that down. And that will be your big M for that equation. And this will be a 2-step equation. Do the same thing for star 2. All right, so from our telescope reading and our chart on page 23, we have all the variables we need to find the distance in parsecs to this star. Again, absolute magnitude is your big M, and that goes into the equation on the top of page 20. And your little m is the apparent magnitude. So it's your apparent magnitude minus your absolute magnitude plus 5, all of that divided by 5. And that will give you an answer, which isn't super important. You will get that log D equals that. And then if you take 10 to the power of the answer you got from the first part, that gives you your distance in parsecs to each of these stars. So fill that in for star 1 and star 2, and then answer the question on the bottom of page 20. And the question is, are these stars members of the Milky Way galaxy of which our sun is part? And then it gives you the diameter of the Milky Way, which is about 30,000 parsecs. So basically what this is asking is, what distance did you find? Is that distance bigger or smaller than 30,000 parsecs? And if it is bigger, what does that mean? And if it's smaller, what does that mean? So are these stars within our galaxy? And once you have done that, that's pretty much all you need to do. So there is a little bit of calculation, a little bit of other things we need to do. It ends up being quite a long lab. And especially if you were to go through and do every individual part, this would be a very long lab. But there's a lot of interesting information here. Pertinent to how you go about making readings about stars, why these readings are important, what they can tell us about the stars themselves, or about what stage of life they're in, how far away they are, if they're similar to our sun, or if they might harbor life. All sorts of interesting things can be found just from taking the spectrum of these stars. Today's lab also gave you a good look about what doing research as an astronomer might look like. We never did get to request time at the big telescope, so maybe if I request some time here, it gives you a pretty snippy message about why you can't. You may reapply in 10 minutes, which is a very weird thing to do. Maybe try on the bigger one, see if that works. Nope. So sometimes this is a bit too realistic. So a 4-meter telescope, I believe like Kitt Peak in Arizona, or some of the Hawaiian telescopes are about 4 meters. A 1-meter telescope would be a pretty good telescope to work on. I can't think of any 1-meter reflecting telescopes, but I believe the biggest refracting telescope was around a meter, somewhere in Wisconsin. So it hopefully gave you a look into some things that might be important to a researcher. But you also don't need to deal with being out in the cold, things breaking down, clouds going through, or anything else. So some good with the bad. I hope you enjoyed this lab. If you did get a chance to do this in class and you're just listening to me for some help, hopefully you had fun and you played around with it and you weren't sticking 100% to what you needed to do. So play with some of the fun things while you're in here. All right, enjoy today's lab and ask your TA if you have any questions. There's a lot to go through in this lab, so don't feel bad if you have questions really about any part that we covered. All right, thank you.